Hi everyone. Okay, I'm this in this session. I'm recording this and I'm gonna upload this to YouTube. So this session, I think the lecture 11 will be divided into two parts. First part about non-convex optimization, and then the second part will be about materialistic optimization, search-based optimization. And after that, we'll have a bonus lecture, which will be about Riemannian optimization. So uh, let me share the screen. Um, okay. So before we start this session, to I want to mention something about. Do you remember in the previous session, I had an ambiguity when I was explaining this slide in the non-smooth optimization. So when we came into the slide 21 in the previous session, uh, we had this cost function and we said, okay, let's consider the jth element of that denoted by Cj, and because we want to take derivative with respect to Bj, and we know that only Cj, we should care about only Cj because the other ones will be just constant with respect to Bj. But the thing is that I was a little bit confused about the last term here. So I thought about it. Now I can explain it better. So when we have this C, consider the jth element. Of course, this is not in terms of beta. Therefore, or will have y transpose y here. These we will consider only the jth element. Therefore, we'll have this term, which is x j transpose y beta j, and note that beta j is a scalar. Therefore, it doesn't matter whether it's on the left part of the x transpose j or on the right. And also here, this term now. The discussion is on this term. This term, if you consider the jth element, so we can consider the jth element of x here and also the second x. So we'll have this quadratic form, beta j x j transpose x j beta. We also can consider the jth element of one of them and the rest of the elements in the other one. So we can have xj transpose only xj of the second one, or xj transpose and the rest of the elements, excluding the jth element. That's why. So the jth element of these can be considered the summation of these two terms, either xj transpose xj or xj transpose the rest of the x, second x. That was the explanation that I had to give you, which I was confusing in the previous session. Okay, also, before I start the non-convex optimization, there is something about integer linear programming in the branch and bound method for integer linear programming, which we discussed during the midterm with the students, but it was a good point, and I want to mention it in the lectures too. So that was the problem: maximize a cost function subject to these constraints, and of course we can solve it. So we'll have something like this. At the end, we'll have these sub problems. So what we are doing is that we consider, so as shown in this tree, so we relax this to be a linear programming. So we disregard the xj and x1 and x2 belonging to the integer set, and if we solve that using the simplex method, we'll have x1 star 8, x2 star is 2.25, and c star will be 35.25. Then we'll consider, so x2 here is a float number, therefore we can consider whether to into two range, which will split that into x2 is less than 2 or x2 is greater than 3. And again, as we have only two variables, we can simply solve it using the visualization method. So by visualization, we can find the extreme points in the feasible set and then evaluate the cost at the extreme points, and find, as it is a maximization problem, find the maximum, the extreme point which has the maximum cost value. And if we do that, we'll have in subproblem 2, which is this problem, which is this problem shown here, we'll have x1 star equals 8, x2 star equals 2, and c star equals 34. And in S3, we'll have x1 star, S3 is this this visualization, where if we solve that, we'll see that S3 equals x1 star is 6.5, x2 star equals 3, and c star equals 34.5. And then again, we can split more. So we can split to x1 less than 6 or x1 greater than 7. Stop problem 4 and 5, I'm showing them here in these figures. So this is sub problem 4 and this is sub problem 5. If you solve them, you will see that sub problem 5 doesn't have any feasible set, so the intersection of the constraints is empty, so it's infeasible. Sub problem 5 and sub problem 4, its solution is x1 star equals 6, x2 star equals 3.25, and c star equals 34.25. Again, we can split sub problem 4 into sub problem 6 and 7 by saying that x2 is less than 3 or x2 is greater than 4. And I'm showing their visualizations here in these two figures. And if you solve them, you will have x1 star equals 6, x2 star equals 3, c star equals 33. For subproblem 7, we'll have x1 star equals 4.5, x2 star equals 4, and c star equals 33.5. But the thing is that a very important thing which you can consider in integer linear programming is that so here, when we reached subproblem 2, we could stop traversing the tree and growing the tree for further levels. We don't need to do that. And we know that the solution, the best answer is actually subproblem 2. Do you know why? Because as we discussed in the session about integer linear programming in the branch and bound method, we said that the more we go in the down in the tree, the more constraints you are adding, right? Like here, we are adding constraints. So the more constraints we are adding to the problem, it means that we are restricting the feasibility set more and more. The feasibility set is becoming smaller and smaller. In the best case, it doesn't change, but it might become smaller. So it means that the cost will be worse. So if we are maximizing the cost by going down in the tree as the feasibility set is shrinking, will have less and less cost. If we are minimizing, the cost will increase. So the higher, the closer we are to the root of the tree, the better cost we'll have. But for example, in subproblem 3, we can't stop because the solutions are not integer points. However, here in subproblem 2, x1 star equals 8, x2 star equals 2, both are integer, satisfying the constraint saying that x1 and x2 are integer. And we have some cost. Of course, this cost is worse than the cost in subproblem 1, which is the relaxation of problem into linear programming. For the same reason that I mentioned, because the feasibility set has shrunk, therefore will have a worse cost than this. Again, we know that we can stop it. comparing S2 and S3, we know that S3 can be continued. However, we don't need to continue that because we know that the solution to the subproblem 3 or the solutions of the children of the subproblem 3 is worse than this level of the tree. And as in this level of tree, we have found an integer solution for the variables, we know that this will be the best answer. And all of these children, even if we found integer solutions for them, they will have a worse cost than this subproblem 2. Again, for example, compare here. This also verifies what I'm saying. So start here in subproblem 6 is 33, but in subproblem 2 is 34. Of course, 34 is larger than 33. So we don't need to continue that. It means that if you don't consider this interesting point, it means that you might go and grow your tree and it for a lot of levels. For example, here you can you if you don't consider that this point, you need to continue subproblem 7 again. You might have a lot of branches, right? And maybe sometimes you may not find pure children which are all integers. But the thing is that integer linear programming using branch and bound is not that much hard because you can always stop at a level where you find an integer solution where the variables are integers. So, and you know that the children of that level will have worse cost. That was an interesting point interesting thing you should note in integer linear programming branch and bound method. In order to have better efficiency and also time complexity of your algorithm, you don't need to continue the tree that much far. Okay, now let's talk about non-convex optimization. Start that. So what is non-convex? First, let's talk about a non-convex optimization function and optimization. What does it mean? So we might have a non-convex cost function. Recall the preliminaries. We talked about convex and non-convex functions in the preliminaries in the first and second sessions. For example, this is a non-convex function. This is also a non-convex function. Why? Because, for example, if you consider these 2 points, if you draw a line between them, this part of the function is above this line. So we know that for a convex function, any 2 points that you choose on the function, if you draw a line between them, that the function will be below that, or at most it will be on the line, but it shouldn't be above the line. Here also, if you consider these 2 points, for example, this part is above that. These 2 points also, this part is above that. So it means that these are non-convex functions. Also, clearly this is a non-convex function. So again, here this is the cost of f, and for example, here we'll have x1 and x2. So we have 2 variables in this figure, and the third dimension is showing the cost value. So, if we want to minimize that, we want to find this point, which has the lowest cost value. If we want to maximize it, so we want to find this point, which has the largest function value. And these are for these cases, we need non-convex optimization, because convex optimization assumes that the function and the cost is convex. Do you remember in the preliminaries, we also defined and introduced the convex optimization. In convex optimization, if you remember, the cost is convex. Also, the cost is a convex function. The constraints are also convex sets. So the feasibility set is a convex set. If either the cost is non-convex or the feasibility set is non-convex, then the problem will be non-convex problem, and we will need non-convex optimization to solve that. And by the way, the credit of this figure is paper 1, reference 1, which we'll see in the references, and that's a paper which about visualization of the loss functions in the neural networks, and it is published in the NeurIPS conference, which is a very important conference in machine learning. Okay, so here consider this optimization problem like this. Minimize the function f subject to yi. So we have m1 inequality constraints, also m2 equality constraints, where functions f, y, and h are not necessarily convex. Okay. Then the introduced optimization methods can also work for non-convex problems. Do you remember so far whatever we were introducing, they were convex optimization methods. However, I can say that although they were convex optimization methods and they were introduced for convex problems, but in practice, they usually work almost well for non-convex problems, although it depends on the problem. So for example, in machine learning and signal processing, I can say that they work almost well. And the reason, for example, for neural networks, I will tell you, I think the next slide, why they usually work well. Because in a nutshell, I can say that in many problems such as machine learning and image processing, signal processing, usually the local minimums or maximums are good enough. But maybe in a problem, the local minimum or local maximum is not good, and you should absolutely find the global optimum. Then in those cases, maybe the convex optimization methods don't work well for the non-convex problems, because they will find a local optimum, and that local optimum might not be good enough. But in practice, in those applications where a local optimum is good enough, then we can say, okay, the convex methods maybe work good enough, well enough for the non-convex problems, because the locals are good enough. Also, the convex problems that if you apply them on non-convex, the convex methods, which we introduced so far, the convex optimization methods, if you apply them on non-convex problems, as I said, they might find good results, but they do not guarantee to find a global optimum. They will find a local optimum, and that local optimum might be local or global. Okay. They can find local minimizers or maximizers depending on the random initial solution. Of course, for example, consider this optimization problem. If your initial solution, because usually you choose your initial solution in the iterative optimization problem, either in first order or second order, when you want to start your iterative optimization, you will start with a random solution, right? But and this random solution should be in the feasibility set. So here you start with this point, with this point, on X. If you do that, then and you will move toward this. For example, you are using gradient descent. So this is the minus gradient. Gradient is in this direction. So minus gradient will be in this direction. And depending on the step size, you might come up and end up with in this point, which is a local minimum. If you choose your initial point to be here, then you will probably end up to this point. If you choose your initial point to be here, then you will also find this point. So if your initial point is here or here, then you will find the global minimum here. If your initial point is here, you will find the local minimum. And if in some practical examples, usually your local is very good enough, like this. So this point, of course, is global minimum. And this point here is your local minimum. However, it's good enough. See the difference between these two is small. But here, for example, the difference is local and global is huge. Therefore, it depends on your application. That's what I'm talking about. The optimization landscape of neural network is highly nonlinear, similar to what we are showing here in this figure. It's highly nonlinear and highly non-convex, but backpropagation works very well for it. So you might be wondering if the optimization landscape of neural networks is very highly nonlinear and highly non-convex. How do neural networks work well for machine learning, computer vision, and different applications on natural language processing? How do they work well? Because they usually in neural networks, the local minimums are good enough, like this case. And you will see why. You will see just intuitively, I will tell you here why. First, before saying that, let me talk about this a bit. So the optimization landscape, what do I mean by landscape? I mean, so when you, like here, when you have some variables and you will have cost. So if you look at it, it's like a landscape with valleys and also with mountains, something like that. So that's why you can call it landscape, although it might be multi-dimensional landscape. So in this case, you have two variables, and the third dimension can be seen as a cost. So it will be like the landscape on the Earth. However, you might have three dimensional variable, and your cost will be in the fourth dimension. So you should imagine it. You can't visualize it on paper. But yeah, so, or you might have multiple dimensions, and you will have one dimension for the cost. And in this case here, I'm also assuming that the cost is scalar. Usually, so far we assume that the cost is a scalar, but again, the cost might be multi-dimensional, right? If the cost is a scalar, the dimensionality of gradient will be the same as the dimensionality of your input, your optimization variables. So for example, in this case, your gradient will be two-dimensional because the cost is also a scalar, but you have two variables. But according to the discussion that we had on the dimensionality of derivative in the preliminaries, do you remember? If, for example, the cost function is two-dimensional, and also your assume your yes, your optimization variable is three-dimensional. So assume you have three-dimensional x1, x2, x3 optimization variable, also two-dimensional cost. So your f will be f1, f2. Then your gradient will be a matrix of 3 by 2 or 2 by 3, depending on what transpose you use. But so it will be a matrix. Yeah, that's one thing I wanted you to know. So that's why we call it landscape. We can call it landscape, especially in the meta-heuristic optimization, and they usually use this terminology a lot, optimization landscape. So optimization landscape of neural network is highly nonlinear and non-convex, but backpropagation works very well for it. But I have a good question here. Assume that usually the loss function in the neural networks, they're usually actually convex loss functions, such as mean squared error. So consider this. B is the batch size. I'm using a mini batch. For example, I'm using mini batch, a stochastic gradient descent, or even Adam. So here I have some batches, mini batches, like B is the mini batch size, and Yi is the output of the network. It's a vector, and Li is a one-hot encoded label, for example, for the ith data in the mini batch. Or what? So you want to minimize the difference between the output of the network and the desired label. It can be one hot or whatever you have. So you can use it, for example, for a regression problem. My point is that this is a convex function with respect to, for example, Yi. So why do we say that the optimization landscape of neural network is highly nonlinear, highly non-convex, and for example, like this? Why? Of course, the mean squared error is quadratic like this. completely convex. The issue is that you shouldn't be confused about it, because this mean squared error or this figure, this is quadratic or this is convex with respect to what? With respect to the yi or li, right? With respect to li, it is convex. With respect to yi, it is convex. However, the optimization variable here is neither yi nor li. The optimization variable in the neural network is the weights of the neural network. It's not, assume you have um, uh, several layers, and in each layer, between the neurons of the any two successive layers, you have connectors, and each connector has a weight, right? So you will have a lot of weights. Not, for example, if you, in the simplest case, assume you have only two layers in your neural network, and each of these lines will have a weight. So for example, in this simple neural network, you'll have 1, 2, so 2 times 3, 6 weights. So your optimization variable will be, in this neural network, will be 6-dimensional. W1, W2, W3, W4, W5, W6. But you might have much, if by increasing the number of layers and the number of neurons, you will have much more weights. So, but your optimization is with respect to these. So you are saying that minimize this cost, let it be denoted by C, minimize C but your optimization variable is WI, I from 1, for example, in this case, to 6. Your optimization variable is not YI. Your optimization variable is not LI. LI is the given in the data set, which is the label. Of course, it's not a variable, but YI, you might think it is a variable because this is the output of the neural network, but you're not optimizing. Your optimization variable is not YI. Your optimization variables are the weights. By tuning the weights, you will generate some YI to have a small loss function, loss value, right? So you will tune your WIs in a way that the YI becomes very similar to LI. And that's why the optimization landscape of the neural network is non-convex and nonlinear, even when the loss function which is used is a convex function with respect to y output of the neural network. That's fine. So that was one thing. Okay. Also, now in this paragraph, I'm explaining why usually in the neural network, the local minimums are good enough. So we can simply use backpropagation, which is, as we discussed before, which is just gradient descent plus chain rule, right? Of course, it will converge to a local minimum, and the local minimum will be dependent on the initial random weights of the neural network. But why usually do they work well even with different random weights? It's because this is the reason. Every layer of the neural network pulls data to the feature space, such as kernels. Okay, so I think it's good for me to visualize it in this way. So consider this neural network. So it goes from 2 to 3, and then again from 3 to 2. Okay. This is layer 1. This is layer 2. So in layer 1, we go from 2 to 3, or 2 and 3 are just examples. For example, it might go from 50 neurons to 150 neurons, but it's increasing. That's my point. So it's when it is increasing, it is like kernels in machine learning. What do kernels do? In a nutshell, I can say that they pull data from Euclidean space to high-dimensional Hilbert space. Okay. In simple words, they increase the dimensionality of data for better separation of classes. So when you have, for example, consider my hand that these two, this is a class, and this my fingers are here are also another class. So by increasing the dimensionality, these two classes to the third dimension, these two classes are separable, linearly separable by a plane. But here, before increasing the dimensionality, they couldn't be linearly separable, right? Because you can't draw a line or a hyperplane between these two classes to separate them. But by increasing the dimensionality, now they are separable. So kernels try to increase the dimensionality for better discrimination of classes or better representation of data. Now in layer 2, you go from 3 to 2, or from more neurons to smaller neurons. And this can be seen as dimensionality reduction. Why? Because we are reducing the number of neurons. So it means that we are reducing the dimension of the data. So every layer is either this or this. It's either going from less number of neurons to more number of neurons, which will be seen as a kernels, or from more number of neurons to less number of neurons, which can be seen as dimensionality reduction. So just you can see a neural network as a stack of kernels and dimensionality reduction, but between them, you will also have nonlinearity, nonlinear activation functions. We discussed these a bit in the session about backpropagation neural networks too. So now let's see every layer of neural network. So it's either kernel or dimensionality reduction. So it maps data to some feature space here. In high dimensional feature space, all local minimums are almost global minimums. This is an important sentence. In high dimensional feature space, in Hilbert space, usually local minimizers are almost global minimizers, because the local minimum values are almost equal to in that space. So in high dimensional feature space, we usually have this case. So the difference of the local minimums is usually small. So we'll have something like this almost. We will not have such cases usually in high dimensional feature space. This usually happens. That's why no matter which initial random point weights we choose, we usually end up with good solution, because they usually have the difference between these FS stars is small. It's not always the case. Sometimes, so first off, they are different a bit. So it's not saying that usually when you start training your neural network from scratch again with different random seed, of course you will have a slightly different solution, because you might end up with another local minimum. However, they usually are the same. And I'm not saying that this never happens, but this is rare. This is rare. This is more often. This happens more often in neural networks. That was the reason. And you can see paper 3 for that, also paper 4, 5, 6. We'll see the references at the end to understand why backpropagation optimization works well in highly non-convex optimization. Okay. Another thing which I want to say, okay, as was explained, so now let's talk about non-convex optimization. The already introduced first order and second order optimization methods can work fairly well for non-convex optimization methods problems for the reasons which I discussed, by finding local minimizers depending on the initial solution of work. Okay. However, there exist some specific methods for non-convex programming or non-convex optimization divided into two categories. So we have two types of non-convex optimization methods. Either they are local optimization methods or global optimization methods. Okay. Local or global. Local optimization methods are faster, but they don't guarantee to find a global minimizer, or if it's a maximization problem, a global maximizer, doesn't matter. But in global optimization methods, they guarantee to find the global minimizer or maximizer, and they can certify that also, whether it's global or not, but they are usually slow to find the answer. So there is a trade-off between these two categories. You want to be fast, or you want to find the actual global minimizer. Okay, an example for local optimization methods is it's sequential convex programming, or SCP. It's an example for local optimization methods. It's based on the sequence of convex approximations of the non-convex problem. So we have convex approximation of non-convex problem, and we do it sequentially, a sequence of them. That's why it's called sequential convex programming, and it's closely related to sequential quadratic programming. If the problem is quadratic programming, recall preliminaries, then we can use sequential quadratic programming, which is a method. And it's used for constraint and nonlinear optimization. Okay. An example for global optimization methods is branch and bound method, which was proposed in 1960s. And it is paper 10. It is an example for the global optimization methods. It divides the optimization landscape. It divides that into feasible, or the feasible set, into local parts by a binary tree, and solves optimization in every part. It's closely related to the branch and bound method, which we use for integer linear programming in the initial sessions of this course. It checks whether the solution of a part is a global solution or not. So it checks that, whether it's a global solution or not. Here, ignore this because I have added that to the slide deck. So I'm going to explain both sequential convex programming and branch and bound method. By the way, another approach for solving highly non-convex optimization is meta-heuristic or search-based optimization, which we will explain later. I think in the second part of this lecture, which will be in another video, I will explain that, introduce that. Okay, so we either should use local or global optimization methods such as sequential convex programming or branch and bound method, or we can use meta-heuristic or search-based optimization. Also, meta-heuristic or search-based optimization, they don't necessarily guarantee that the solution is global minimizer, similar to what we have in local optimization methods. However, global optimization methods such as branch and bound method, they can guarantee finding the global solution. Okay, now let's talk about sequential convex programming a bit. By first introducing the convex approximation. So what we have is this. Recall equation 1, where we are minimizing a function f of x subject to it, and these are the constraints. We have m1 inequality constraints and m2 equality constraints, denoted by yi and hi, respectively. So sequential convex programming, or SCP, it iteratively, so it's an iterative solution optimization method. It's iteratively solves a convex problem where at every iteration it approximates the non-convex problem 1. So this is a non-convex problem because maybe f is non-convex, yi may be non-convex, or hi may be non-convex. It means that either the cost is non-convex or the feasibility set is a non-convex set. So, and but sequential convex programming, iteratively, in each iteration, it approximates it to be convex, so it relaxes the problem to a convex optimization problem, and it solves that sequentially. But there is so based on the current solution, it restricts the variable to be in a so-called trust region. So it uses a concept named trust region, which we'll introduce soon, in order to make sure that we are not very off topic. We are not going somewhere which is not trustworthy, because we know that the optimization method that we are tackling is actually non-convex. We are relaxing it So we need to have a trust region to not go off much. Okay, the trust region makes sure that the variable stays in a locally convex region of the optimization method. So again, what does trust region do? It makes sure that the variable, the optimization variable, stays, which is the solution of that iteration, it stays in a locally convex region. So locally convex region of the optimization problem. That's why it's a local optimization method. At iteration k of the SCP, we solve this optimization problem. So at each iteration, we are relaxing this problem to problem 2, to equation 2 here. So f hat of x here is a convex approximation of f of x. Y I hat of x is a convex approximation of yix, and hi hat x is a convex approximation of hix. So we do it for all of the constraints and the cost function. We approximate them. We have convex approximations of them, and we'll see how we can do the convex approximation. And what is here? You're also saying that the x needs to be in the trust region in the kth iteration. So t is denoting the trust region at the iteration k, tk. Why do we do that? Because we want to make sure that the variable stays in a locally convex region in the optimization problem. Okay. This approximated convex problem, which is equation 2 here, is also solved iteratively itself. So this also is solved iteratively using one of the previously introduced methods, such as the interior point method. So we can use any of the optimization methods which we introduced so far to solve equation 2. Why? Because we know that equation 2 is a convex optimization problem, and whatever we introduced so far in this course were convex optimization methods for solving convex optimization problems. And we know that equation 2 can be solved by them, such as by interior point method or Lac barrier method. So we can solve them. And an interesting thing is that here we are doing in SCP, we are doing it iteratively, and at each iteration we have to solve equation 2, something like that. And it means that we have nested loop. So we have one loop for SCP for iterations of the sequential convex programming, and in each iteration of SCP, we also need to solve a convex optimization problem, which itself is solved by an iterative optimization method, such as interior point method, which is an iterative method, right? So we have a nested loop. There exist several approaches for convex approximation of the function. In the following, we introduce some of these approaches. For now, in the next slide here, we are gonna explain how we can do the convex approximations, how we can find f hat of x from f of x, or yi hat of x from yix, and hi hat of x from hix, right? Okay, let's do that. For that, we can use Taylor series expansion in this way. The non-convex functions f, y, and h can be approximated by affine functions or first-order Taylor series expansion. Do you remember affine is just a linear function which might have a bias, right? Therefore, it's first-order Taylor series expansion, which is a linear thing. And we can use that, to make it convex, because we know why. Why do we know it's a convex? Because we know a linear function is always convex. A line or a hyperplane is always convex, a convex function. So, for example, the function f is approximated as this. So f hat of x can be this. What is this? This is the first order Taylor series expansion of f of x, right? And this is a so f of xk at the evaluation of f at xk plus gradient of f xk transpose x minus xk. So this is the first order Taylor series expansion around the point xk. Okay. Or we can use more accurate approximations like quadratic functions, which is the second order Taylor series expansion, to make it convex. For example, the function f can be approximated by this. So again, this is the second order Taylor series expansion of the function f around the point xk. Xk is the solution of the problem at the iteration k. So this f of xk, gradient of f of xk times transpose x minus xk up to here, these two terms is the first order Taylor series expansion, but we will have a third term, which is the quadratic term for second order Taylor series expansion. And what is p here? It's projection. So projection, do you remember we had projection? We introduced that in the session about proximal methods several, I think 3 sessions ago. So P is this projection of the Hessian onto the symmetric positive semi-definite cone. So first off, we need to have Hessian here because it's a second order derivative in the second order Taylor series expansion. In the third term, we need, so in the second term, we need to have gradient. In the third term, we need to have the Hessian. In the first term, we have the function. In the second term, we have the gradient. And the third term, we have the Hessian. But the Hessian, we know that needs to be positive semi-definite by definition. Therefore, if it's not, we need to project it onto the cone of his semi-definite cone. How do we do that? Can we do this projection? Simply, we can. What is the definition of positive semi-definite matrix? It means that its eigenvalues are non-negative. They are either 0 or positive, right? So for this projection onto the positive semi-definite cone, we can simply have the eigenvalue decomposition of the matrix P here, or the Hessian here, and then set the eigenvalues which are negative to be 0. So we can have, for the eigenvalues, we can have maximum of each eigenvalue and 0. So if the eigenvalue is negative, we make it 0. If it's 0 or positive, we use that. Then we reconstruct the eigenvalue decomposition in order to have the matrix back. This is the projection onto the positive semi-definite cone. Okay. And the same approaches can be used for approximation of fyi and hi. So this was the approximation for f. We can do the same for yi, hi. We can have either first order or second order Taylor series expansions of these to have yi hat and hi hat, right? Okay. So, and y, by the way, is a quadratic form convex, because we know that the quadratic form, quadratic function is a convex function. So either affine function or quadratic function approximation makes the functions convex. Okay, now so we can have another method for another approach for convex approximation using the particle method. And what is that? We can approximate the functions f, y, and hi in the domain of the truss region using regression. This approach is named the particle method, paper 7. So consider this. And what are these? The endpoints which lie in the truss region. So you have a truss region. Locally, what is the truss region? A local convex region around the point, okay? And assume we have endpoints in that truss region. We can use least squares quadratic regression. So why do we say least squares So this is exactly the least squares quadratic problem. Why is it quadratic? Because we have power 2 here, and it's least squares regression because we are minimizing this quadratic form. And what is this? To make the functions convex in the truss region. So we are saying that, consider this. This is a quadratic problem with unknown P, B, and A. These are the parameters. or the optimization variables. We want to find these. And we want this quadratic function to approximate or regress the function f the best. So this minus this is the error of this quadratic function from the function f, and we have the squared error, and we want to minimize the squared error over the m points. We're subject to when we know that the p should be positive semi-definite, right? Okay. Then the function f is replaced by this. So after solving this and finding p and a and b, we can simply say, okay, this now is a good approximation of f. Therefore, we can replace f with exactly what we have here with the found parameters p, b, and a. So p is a matrix, b is a vector, and a is a bias, a scalar bias. By the way, why should we have p positive semi-definite? Because, of course, this needs to be a positive semi-definite for this to be a convex function. So because this is the quadratic function, and the quadratic function needs to be facing up in order to be convex, like this, right? Here. If p is negative definite or negative semi-definite, then the quadratic function will be facing down, which is not convex anymore. It's concave, actually, opposite of convex. It's concave, and therefore that's why we need to have p positive to be positive semi-definite in order for this to be facing up, this quadratic function to be convex. Again, don't forget we are having convex approximation, so this approximation should be convex. Okay. Again, we can do the same for yi and hi. So here we'll have yi and hi in this term in order to have approximations of yi and hi in particle method. Another approach to have convex approximation is quasi-linearization. So what is that? We should state that the function f, we should state it in this way. So we can say f of x equals a of x times x plus c of x. Okay, now let's see what these are. For example, we can use the second order Taylor series expansion to do this. For example, again, we can write f as x transpose px plus b transpose x plus the bias a, where p is positive semi-definite. So this is a convex quadratic function facing up. So we can, this is a second order Taylor series expansion. Therefore, we know p, b, and a, right? Recall here, this is, we know what p, b, and a are in the Taylor series expansion. We can rewrite or restate this as this. Why? Because here, consider this will be equal to 1/2 x transpose p. Note that p is a symmetric matrix, therefore p transpose equals p. So this will be x transpose p transpose, but p transpose equals p itself, plus x. It is multiplied by x plus b transpose x. Right? That's why we can write these two terms as this, and we also have plus a. Okay. Now let's consider a to be this. Comparing this with this gives us to take makes us get 1/2 px plus b transpose to be a, and cx to be a to be cx, right? Okay. And they, of course, depend on the Taylor series expansion of f. Hence, the convex optimization function, approximation of function f can be this. Can be written as this. The same approach can be used for yi and hi. So we can do the same for yi and hi in order to have this approximation. It's interesting that you should note some difference between these approaches. So in the first approach using Taylor series expansion, also in the third approach using quasi-linearization, we already know a and b and p from the Taylor series expansion, right? However, in approach 2, which is the particle method, we find A and B and P using regression by solving this optimization problem. So this is a subtle difference between these. Also, why do we call this quasi-linearization? Because we are writing a quadratic form like a linear form. So consider A to be it's like ax plus b in this form, right? If you consider a of x, although a of x also itself depends on x, but if you see a of x, capital A of x, as a black box, then it seems to be like a linear function. But it's not an actual linear function because a itself has x in it. So it is an actual quadratic function. But as we are showing it in a linear format, we can call it quasi-linear, right? That's why it's called quasi-linearization. Okay. Now, so we introduced three methods, three approaches to have convex approximation of f, y, and h using either Taylor series expansion or particle method or quasi-linearization. Now let's talk about truss region. Truss region, do you remember what was truss region? Here we talked about it. Truss region makes sure that the variable stays in a locally convex region of the optimization problem, right? Which we are also having in this optimization problem. In every iteration of sequential convex programming, we have a truss region. Okay, let's see how we can formulate that. Formulation of truss region. The truss region can be a box. By box, I mean a cube, a hypercube in multiple dimensions, right? A box or a hypercube around the point at that iteration. This. What is this? So this is a truss region at iteration k. What does it mean? It means that x, what does it mean? For first off, let's consider one of the dimensions. So j goes from 1 to d. So here we are talking about element-wise. Each element, the jth element or jth coordinate, xj minus xj k. So all of the points whose jth coordinate has a distance less than rho I from the jth coordinate of xk. Xk is the point at or the solution at the kth iteration. Okay, so xk is known, but now we can find the points which are close to it by having a box around it. So assume that, for example, in 2D, this is row 1, row 1. So if x1, so this is x1k. This is x2k. So xk has coordinate 1 and coordinate 2 in 2D, right? So here in the first dimension, we'll say that accept all of these region where points are row 1 by row 1 away from x1k. Also for x2, for the second dimension, we are saying that, okay, assume this is row 2, this is row 2. Accept the region here. All of the points here. Now the intersection of these two is just this box. That's why we are saying it's a box or a hypercube. Now you go to multiple dimensions and you will have hypercube, right? So this truss region can be a box or a hypercube. And xj and xjk, we said that this jth element of x and xk. And note that x and xk are vectors, d-dimensional vectors. Okay. Rho I is the bound of the box for the jth dimension, shown here, for example. Okay. Another option for trust region, so it can be either box or it can be ellipse. So we can have quadratic trust region. Rather than hypercube, we can have ellipse around the point to have quadratic trust region like this. So all of the points which are in the neighborhood of xk inside an ellipse. So for example, this is x in 2 dimensions. For example, it can be something like this. This ellipse might be, in some cases, if you consider rho to be the same for all dimensions, then it will be like a sphere, or as it is also we are considering inside of it, it will be a ball, right? But anyways, it's either ellipse or a ball around the point xk. So the trust region can be hypercube or ellipse or ball. And this P also is a symmetric positive definite because it's showing an ellipse, and rho is a radius of ellipse. Okay. Now, so after formulating the trust region, how can we update the trust region in each iteration? Okay, because the trust regions of iterations are different. Note that T of has a superscript K. It means that in each iteration we might have different trust region. Now we need to update that. Okay, the trust region gets updated in every iteration of sequential convex programming. In the following, we explain how the trust region can be updated. Okay, recall equation 1. I think I have repeated here. Okay, here. So we are minimizing the function f with M1 inequality constraints and M2 equality constraints, and these are not necessarily convex. So this optimization problem is a general optimization problem, which might not be a convex optimization problem. Then we can embed the constraints in the objective function like this. Do you remember one technique in optimization was soft penalty, where we are embedding the constraints into the cost function, similar to the approach that we had in Lagrangian. Okay, so now minimize phi of x, which is the regularized cost function, where the cost is this, and we have a regularization term or a penalty term. This is the inequality constraints, and this is the equality constraint. And do you remember this technique? So we had this technique, we introduced that, I think, in the sessions about distributed optimization. I said there is a good technique for converting inequality constraints to equality constraints by saying that let's yi prime of x be defined as maximum of yi x and 0 equals 0. So this is an equality constraint. And why is this equivalent to this? Because if yi is less than 0, then it will be 0, satisfying this inequality. If it's greater than 0, which is not satisfying this inequality, then this will not be equal to 0. So it will not satisfy this equality constraint as well. That's why these two are equivalent. Now, we have converted this to this, and then we have put it in the penalty term. We can write this in this way, where we are having a quadratic format of this equality constraint. Why? Because we want to have quadratic forms of these constraints, penalties, because quadratic has a simple derivative. And lambda is a regularization parameter. Also, this technique is called exact penalty method, proposed in 1994, because it penalizes the violation from the constraints. So this is the technique this is the soft penalty technique or regularization technique, which is here we can call it exact penalty method, proposed in 1994. Okay. For large enough regularization parameter, which gives importance to violation of constraints, of course, so lambda is the regularization parameter is giving weight to the violation of constraints with respect to cost. So the more the lambda, the more you care about violation of from the constraints. So for large enough regularization parameter, the solution of problem 9 is exactly equal to the solution of problem 1, and that's interesting. So theoretically, it has been shown maybe in this paper 12 that if you solve this for large enough lambda, it is exactly equal to this, and hence the name exact here, exact penalty method. Okay. Now recall equation 2. What was this? This was the convex approximation of this problem, where we had the approximation of f, y, and h as f hat, y hat, and h hat respectively. And we also had these for the thrust region. Okay, we also had this in the previous slide, which was this equation 9. I have repeated it here. Now, similar to this, we can define this. What is this? So here it's the same as this, but I'm replacing f with f hat, y with y hat, and h with h hat, right? So I'm defining this for this problem. This was defined for this problem, which was non-convex. But this is defined for this, which is a convex approximation. Okay. At iteration k of sequential convex programming, let x hat k be the solution of the convex approximated problem 2. Assume that at iteration k, its solution, the solution of this problem, which is the convex approximation of the actual problem, let its solution be denoted as x hat k. Okay, using any method such as the interior point method. Okay, we calculate. Now we know that we can simply find x hat k using any of the methods introduced so far in this course, such as interior point method. We can now calculate the error, because we know that there is a difference between phi hat x hat. So feed these to these phi hat. Also, we know that if we solve this problem, actual problem, it will give us some xk. We can feed it to this phi x. So we'll have phi xk and phi hat x hat, right? So there is some error. And we know that this should be decreasing. This should be decreasing. Yes. Now let's see, we are defining two things. Delta hat and delta. What is the delta hat and what is delta? So in both of them, the first term is phi of xk. So this is phi, defined here. And xk, what is xk? It's a solution. It's a solution to the actual optimization problem at iteration k. What is x hat? X hat is a solution to this optimization problem, approximation. Y hat is defined here. But the difference is that in delta hat, we have phi hat x hat here in the second term. In the delta, we have phi x hat. So we are fitting x hat to the phi here. This is the difference between these two. Okay. This is called predicted decrease. This is called the exact decrease. And they both should be decreasing. Okay. Again, I have repeated the sentence here. We calculate these two. Two cases may happen. Okay. What are these cases? We may have progress in optimization. We have progress in optimization if we have this. What is this? So A delta hat is less than or equal to delta, where A is between 0 and 1, such as 0.1. In this case, we accept the approximated solution. So give me a second. Sorry guys, Yeah, I paused a bit and thought more about it to explain a bit better this part. So what I said was almost correct, but let me recap what I said. The thing is that here, okay. So we have this function as phi of x. What is this? It's just a regularized cost function of the actual problem, which is a non-convex optimization problem, right? Like phi of x. We also are saying that let's have the phi of x version, but for the convex approximation of the functions. So we have f hat, y hat, and x hat, and let it be denoted by phi hat of x. Okay. So far good. Now we are assume that we are in the iteration k plus 1. Okay. So we are in iteration k plus 1, and assume we have the solution from the previous iteration of k in the sequential convex programming, right? So we have some solution xk superscript from the previous solution from the previous iteration of sequential convex programming. Okay, now we are in iteration k plus 1. So x superscript k, we have it from previous iteration. We have phi of x defined here. This is a function, just ignore this minimization for now. Okay, we also have phi hat of x defined here. This is another function, right? And these are the Taylor series, maybe expand approximations of these or other methods for approximation of these yi, hi, and f here. Okay, now what is x hat? What is x hat? We solve this in iteration. In this iteration, let's solve this in iteration k plus 1. Let's solve this optimization problem. This is a convex optimization problem. We can solve it using any method introduced in this course, such as interior point method, because it's a convex optimization problem. Let's its solution be x hat. Okay. Now we can calculate delta hat and delta here. How? So we know the functions phi and phi hat. Here we feed x hat, which we found here, into phi hat. We also have xk from previous iteration. We feed it to function phi. So this is a scalar. This is also a scalar. Delta hat is a scalar. It's the error between phi of x and phi hat x hat. We also have this delta, which is we feed xk from previous iteration to phi, function phi. We also feed x hat, which is the solution of this, to the function phi again this time. This is also an error, a scalar error delta. Okay, what are they showing actually? I have repeated them here again. What are they showing? This delta hat is showing the difference between what is phi. Phi is actually a reformulation of the actual optimization problem where we are embedding the constraint into the cost, right? Phi hat is the reformulation of the approximated optimization problem. So phi, you can see it as the actual optimization problem, reformulated. Phi hat, you can see it as the convex approximated optimization problem, reformulated. Okay. Of course, we want phi x to be similar to phi hat x. Phi hat x is the approximation. But we can have two types of errors, again, as we have here. We can have phi, so phi of xk is the cost up to now, cost up to the solution of the previous solution iteration. Okay, that's why we in the first term of both of these errors we have phi of xk. Okay. However, we can have its error or its difference from phi hat x hat or phi x hat. So we can feed the solution of this optimization problem to either phi hat or phi, right? We have an approximated solution, but we can fit this approximated solution to the actual problem or to the approximated problem. That's the thing. Okay. Delta hat is the error from the evaluation of the approximation in the approximated functions. Delta is the error from the evaluation of actual problem. From the evaluation of actual problem at the approximated solution. Okay, that's the thing. Now let's see. Of course, here we are saying that if alpha delta hat is less than delta, and alpha is between 0 and 1, for example, 0.1, it means that if delta hat is less than, for example, 10 times delta, okay, then it's good. So if delta hat is less than a scale of delta, this error, it's good. Why? Because phi hat x hat has more approximation level than phi x hat. Do you know why? Because x hat, we know that is the approximated solution. Phi hat is the approximated problem. So it's error into error. Error of the solution into error of the approximated functions. This is phi hat x hat. But phi x hat has one error. One error, which is the approximated solution. So phi hat x hat has error into error, propagation of errors. Why? Because x hat is some error in itself. Phi hat also has some error because of approximations of functions. However, phi x hat, phi is the actual optimization problem regularized, but x hat only has error. Okay, that's why if the approximated error, which has error into error, has less error than some scale of this actual error, which has only one order of error, then it's good. Then it's good. Then accept this x hat for this iteration k plus 1, accept it. And also reward the trust region. You say, okay, the trust region was good, therefore let's expand it. So multiply this. Do you remember rho was the size of trust region, either in the box or in the radius of the quadratic trust region, right? Here or here. So expand rho, it means that enlarge the trust region. It's good. It's trustworthy. Let's enlarge that. However, if this delta hat, which is a harder error, so which has error into error, is larger than some scale of delta, right? Larger than 10 times, because alpha is 0.1, so it means that delta hat is greater than 10 times delta. It means that if the error which has error into error, it has propagated error in itself, is larger than a scale of this actual error, which has only one order of error, then it's not good. Then it's not good. Reject the solution, reject the approximated solution, which was x hat, and have the previous solution, copy it to be the solution of the iteration k plus 1. So copy the solution of iteration k to be the solution of iteration k plus 1, right? And punish the trust region, making it smaller by multiplying it by gamma, which is between 0 and 1. So rho becomes smaller. It means that the trust region becomes smaller, right? So in summary, the trust region is expanded if we find a good solution. Otherwise, it is made smaller. So in summary, if we find an approximated solution, which is actually decreasing the error, it's good. It's a good solution. Accept it. Enlarge the trust region. If it's the approximated solution X hat is not decreasing the error good, well enough, reject it. Copy the previous solution to be the solution of this iteration, and make the trust region smaller. Of course, by making the trust region smaller, you're changing this optimization problem, and your X hat solution will be different again. So don't tell me that how is it different? How will it be different? In the next iteration k plus 2, we'll also have the same X hat and we'll get stuck in this case. No, because when you make the trust region smaller, your constraint here will be different. And when you solve it using the interior point method, for example, you will have another X hat. Therefore, hopefully that X hat will fall into this case, which is a good solution, and you accept that. We get it. And by the way, comparing delta hat and delta, I think we usually expect that delta hat is larger than delta, or it's worse than delta, I can say. Why? Usually, because it has error into error. It has propagation of error into it. It has solution X hat, which is approximated solution, into other approximated functions. However, here we only have approximated solution. Okay, that's why here we are kind to delta hat. We are saying that if delta hat is less than some 10 times delta, we are kind to delta hat because we know that delta hat is much worse, would be worse than, usually worse than delta. So if it's less than 10 times delta, then it's good. If it's worse than 10 times delta, then it means that it's bad. Okay, that's it. Okay, I think we needed to talk about this in detail so you understand the concept of trust region and also the sequential convex programming. Now sequential convex programming is over. Let's start the branch and bound method, which was an example for global optimization method for solving non-convex optimization problems. The global optimization methods guarantee that they will find a global solution. They can certify it, but they are usually slow. In contrast to the local optimization methods, such as sequential convex programming, which we discussed, and they are the local optimization methods are fast, but they don't guarantee that they find a global solution. But this is usually slow, branch and bound, but it guarantees that it finds a global solution. Okay, it's closer related to the branch and bound method, which we introduced for integer linear programming. Let's see. It was proposed in 1960. It is a global optimization method, branch and bound I'm talking about. It is slow, but it finds the global optimum. Okay. The idea of this method, okay, it says divide, this is the idea of this algorithm. Divide the feasibility set, so we have some feasibility set region, right? Into two convex sets, or rectangular or hypercubic regions, okay? In high dimensionals, you can see that's hypercubic. In each region, then, find an upper bound and a lower bound for what? For f star. So f, assume, is a cost function. You assume you want to minimize the cost function. So you have an optimization landscape. You will have some feasibility set because of the constraints. Divide the constraint into the feasibility set formed by the constraints into two regions. In each region, find some upper bound on f star and lower bound. So sandwich f star in some range and say that f star can't be above some upper bound and can't be below some lower bound. And we'll talk about how to find that upper bound and lower bound in each region. Okay, now when you do that, choose the better region among these two. Which region is better to continue branching? Go into that region and do it iteratively and split it again. Do it iteratively so it's As you see, it's a recursive procedure. So when you code it, you need to do it recursively and do it until convergence. Of course, it's a tree because you can implement tree using recursion in coding. Okay. Now, approximation of lower bound. So for approximation of lower bound, what do we do? Lower bound of f star in a region. It can be the solution of a convex relaxation of the optimization problem. Why? Because we know that the solution to the problem, which may be non-convex, is worse than the solution to the convex relaxation of that optimization problem. So in other words, when you have a non-convex optimization problem, when you relax it to be convex, your solution, if you, for example, if it is minimization, your solution will be better, will be less than f star. So assume you have problem 1, it is non-convex. You relax it to be problem 2, it is convex relaxation of P1, okay? This gives you, assume F1 star. Assume this gives you F2 star. If it is a minimization problem, or minimization problem, you know that F2 star is less than or equal to F1 star. It's better because it's a relaxation, a convex relaxation. If it is a maximization problem, you know that F2 star is greater than or equal to F1 star. So it's better again. So convex relaxation makes the optimal cost better. That's why now we are here, we are talking, assuming that this is a minimization problem. Therefore, for lower bound, we can consider the solution of convex relaxation of the optimization problem in that region to be the lower bound on F star because of this. Okay. For upper bound of the optimal value F star in that region, it can be any point in the region. Why? Because this is by the definition of the global minimum of F star. Global, what is definition of global minimum of function f, which is F star? It means that F star is less than or equal to f of x for all x in that region, in the domain, right? This is a definition of global minimum. So if you take any point in that region, in that domain, of course it's greater than or equal to F star. So any point you can take it as the function value at that point can be the upper bound. Okay, so now we talked about these, how to have the upper bound and lower bound in each region. Okay. And also another thing which we should note is that the more we progress in the algorithm, the closer or the tighter the lower bound and the upper bound get to each other. So initially, maybe if you assume I denote lower bound by L and upper bound by U, initially U might be here and L might be here. So these are scalars, right? Because these are F values. Sorry. The difference between these two is huge, but gradually when you go progress in the iterations of the branch and bound method, U and L get closer to each other, so they become tighter. So this range becomes smaller, or this sandwich becomes smaller, right? Okay. Until they can reach each other, and that would be the actual F star, because we'll have when we have F star between L and U, and when U and L are equal to each other, it means that the F star, when it's sandwiched between two equal numbers, it's exactly those numbers, right? That's the thing. Okay, now let's see the branch and bound algorithm in detail. Okay, so start with the feasibility set as a region. So consider the region that you wanna split to be the feasibility set. defined by the constraints of the optimization problem. Okay. Calculate the lower bound L and upper bound U of the feasibility set, right? Set the overall. So we define overall lower bound and also overall upper bound denoted by L overall, lower bound overall, and U overall, upper bound overall, to be the lower bound and upper bound of the feasibility set. How do we, by the way, calculate the lower bound and upper bound of the feasibility set using these 2 points that we talked about? For lower bound, we can consider the convex relaxation. For upper bound, we can consider any point. So do that, and then L overall and U overall are initialized to be L and U in the feasibility set. Now we have a loop over iterations. We have it because it is an iterative method, right? Split the region, the region. So initially the region is feasibility set, but later on the regions becomes smaller and smaller. Split the region into left and right regions. So by left and right, here I'm just for the sake of notation I'm saying that, but it's not necessarily left and right because in multiple dimensions, in high dimensions, there you can't define any left and right. I mean into 2 regions, okay? But for the simplicity, I named them left and right regions, okay? And why do I call it left and right? Because it's actually a binary tree. So assume this is the region, you can represent it by a binary tree. You split it into 2 regions where the union of these 2 regions is this, and they don't have any intersection. So it means that the disjoint union of these 2 regions, subregions, is the actual region, right? Divided into these 2 regions, I call it left and right regions. Again, calculate, okay, yes, the lower bound and upper bound of left and right regions. So in each region, calculate the lower bound and upper bound. Let the lower bound and upper bound of the left region be denoted by L left and U left, respectively. Also, for the right region, we denote them by lower L right and U right for lower bound and upper bound, respectively. Okay. So we have these 4 scalar values. Update the overall lower bound if the largest lower bound among left and right regions is larger than the overall lower bound. In simple words, let update the L overall, which was initialized by this, the lower bound of the feasibility set, to be maximum of L left, L right, and L overall. What does it mean? It means that between L left and L right, which one is better? Of course, the larger one. The larger one. That's why I called it largest lower bound among left and right. Why? Because it means that for tighter range, do you remember we want the range between lower bound and upper bound to be tight. It means that for tighter range, we want larger L and a smaller U. We want larger lower bound and a smaller upper bound to make it tighter. Therefore, I like the lower bound to be larger. So when I'm comparing the lower bound of ref region and right region, I take the largest one. And then I'll also compare it again to the overall lower bound. And again, I take the largest one. So in simple words, I take the largest among L left, L right, and L overall. I update that. Do the same for the upper bound, but in this case, take the mean. Again, for the same reason. For tighter bound between lower bound and upper bound, tighter range, I want a smaller upper bound. Therefore, I get the smallest upper bound among left and right region. Also, do it the smaller of overall upper bound and them. So in simple words, I take the smallest or minimum between U left, U right, and U overall, and update U overall. Okay, it means that by these 2, it means that gradually the distance between L overall and U overall is decreasing. Why? Because U overall is getting smaller and smaller, and L overall is getting larger and larger. if U overall and L overall, their distance is less than epsilon, of course, L overall can't get larger than U overall. In the best case, L overall will reach to be equal to U overall. So there is always a gap, which this gap might become zero. But as long as it becomes smaller than some small epsilon value, then terminate. So this is a convergence criterion or termination criterion. Okay, terminate, and then if this happens, terminate. And after termination, if it is minimization, return L left. Oh yeah, if it's minimization, okay. And if it's L left is less than L right, lower bound of left region is less than lower bound of right region, return L left. If lower bound of right region is less than lower bound of left region, then return L right. And it's X star, corresponding X star. So L left and L right are F star, right? And also they have corresponding X star. So X star is the optimum optimization variable, and F star, which is either here L right or L left, is the optimum function value, cost value. And this is for minimization. And why do we do that, by the way? Of course, for minimization, we want smaller F star. That's why if L left is less than L right, we return L left and its corresponding X star. If L right is less than L left, it means that its F star is smaller. So return that and its corresponding X star. That's the thing. For maximization, do the reverse. We don't. We should return for maximization. Yeah. Yes, you should, then the comparison should be the other way around. So if L left is larger than L right, then you need to return L left and its corresponding X star. Okay, that's the thing. And by the way, as the range is, this range has become tight, so you might be wondering, why are we returning lower bound rather than upper bound? For two reasons. First off, there is no much difference between upper bound and lower bound because they are getting very close to each other. Second, it's better for minimization. We usually want to return the lower bound, smaller F star. For maximization, you might, if you want to return an upper bound, then you need to compare U left and U right. It depends on you, but I think you got the idea what I mean. So for maximization, you care about L left or U left if which U or L of the region which has larger U and L or F star. For minimization, you care about the region which has smaller U and L, okay? Because U and L are in the essence of F star. Okay, that's the thing. By the way, we in branch and bound, we can continue in the region. So yeah, I think I need to mention here in one of these steps that you choose when you are going to split a region, you should choose between the children. You can choose the one which has better solution. So you don't. This is my guess, but I might be wrong. But I think I'm right that you should choose the region which has a smaller cost function if you are minimizing. But you can always, in order to make sure and guarantee that this is a global solution, you can go over all of the branches so to have a complete binary tree. If you do that, then you can guarantee that you will find the optimal global solution among all of the children at the end, right? But if you don't want to guarantee that, and if you want to be more efficient and faster, then maybe you can continue in one of the branches which is the best branch, the best regions in each iteration. That's the thing. But if you want to make sure you sacrifice the speed, of course, this is a slow method because it's a global optimization method, and you can go have a complete tree. Okay. So I talked about sequential convex programming as a local optimization method and also branch and bound method as a global optimization method. Before I finish that, let me say I have also, it was one of my first papers. I have a paper related to branch and bound method, but I proposed a tree-based optimization. I called it TBO, short for tree-based optimization, with for meta-heuristic methods. So I said, if you search tree-based optimization, its title is tree-based optimization, a meta algorithm for meta-heuristic optimization. So the branch and bound method here is for classic optimization, but I said, okay, what if we have meta-heuristic optimization like a PSO or genetic algorithm, which I will explain in the next session, next part of this session. And I said, okay, let's have a tree or branch and bound, but in each child of the tree, let's solve a meta-heuristic optimization method. Of course, in that case, we might get stuck in one of the local optimums. Therefore, I did it stochastically, so I had a probability on whether I accept that or not, and I need to do it for several trees, for several different trees, to make sure that this is a good solution. You can look at that, that you might find it interesting. That was one of my first method papers. Okay, acknowledgement. Some slides of this slide deck are inspired by the lectures of Professor Stephen Boyd at the Stanford University. And also our tutorial has the materials of this slide deck, which is paper 13. Okay, let's look at the references in this slide deck. So this paper visualizing the loss landscape of neural nets. It was published in NeurIPS. So as I said, the loss landscape, the optimization landscape of neural networks is highly nonlinear and highly non-convex for the reasons that we explained, and you can visualize them. This paper has discussed it. Also, this is our paper on kernels. So reproducing kernel Hilbert space, Mercer's theorem, eigenfunctions, Nystrom method, and use of kernels in machine learning. You can look at that. I cited this for explaining. Do you remember I was saying that when in layer of neural network, when we go from smaller number of neurons to more number of neurons, it's like kernel. So you can take a look at this to know about kernels. Also, this paper is saying that why in neural networks almost all local optima are global. Do you remember I talked about it? Okay, this paper talks about optimization landscape in shallow neural networks. This is a very good and interesting paper which discusses why neural networks work. Have you heard of people saying that we don't know why neural networks work? We actually know. This is a theory. You can go and see this paper is published in IEEE Transactions on Information Theory, published in 2018, and it discusses the optimization landscape of neural networks. It's using probability bounds and also pack learning and these things. Also, this paper was generalized to deep neural networks. So this was for shallow neural networks, but this became deep here and it was published in the conference, NeurIPS conference, by some other people. And this, let me see, a convergence theory for deep learning via, this is also talking about the optimization of the deep learning. these are the papers which talk about why neural networks work in the optimization world using probability bounds and etc. This is the paper of Boyd talking about sequential. No, sorry, this is the lecture of Boyd talking about sequential convex programming, and I think it's very useful. You can take a look at that. Also, you can watch his YouTube video about sequential convex programming, explaining this slide deck. Okay, and this local convergence of sequential convex programming for non-convex optimization in 2010. So it talks about the convergence of SCP or sequential convex programming. And do you remember I said sequential convex programming is closely related to sequential quadratic programming, and that was proposed in 1995. Also, this an automatic method for solving discrete programming problems, 1960. What was this for? Yeah, this was the branch and bound, the paper which proposed the branch and bound method. That's an interesting thing by Land and Doig. Also, this is a paper in Xi'an about trust region methods. So you can see it as a kind of a survey. This is exact penalty methods. Do you remember? Here we talked about saying that this is like the soft penalty method, where we said when we increase lambda, we'll have the solution of this will be exactly equivalent to this, and that's called exact penalty method. And this is its paper 12, proposed in 1994. This is also our tutorial paper on optimization, which has some of the materials in this slide deck. You can take a look at that. Okay, this session is over, which was about non-convex optimization, and we talked about the two families or two categories of methods for solving non-convex optimization, which are local methods such as sequential convex programming and global methods such as branch and bound method. There is another way to tackle non-convex optimization problems, although it doesn't guarantee that it is a global solution. That's materialistic or surface-based optimization methods. We'll talk about it in the next video, part 2 of this lecture. And yeah, that's it. Thank you for your attention.